Thank you, everyone, for joining us tonight. Our speaker is Dr. Annmarie Eldering, visiting us all the way from the other side of Pasadena at JPL. Long drive over, probably against rush hour traffic, too. Dr. Eldering completed her PhD at Caltech in environmental engineering science, focusing on air pollution in Los Angeles. After a few years as an assistant professor at the University of Iowa, she came back to California to teach at UCLA and then joined JPL as a research scientist. She has worn many hats at JPL: research scientist, section manager, project scientist, principal investigator, and a bunch of other ones. Dr. Eldering has applied her expertise in radiative transfer and light scattering to many missions and different studies. In 2010, she joined the Orbiting Carbon Observatory-3 mission, and now is the project scientist for the OCO-3 mission. Today she's going to share with us some mission news, some progress, and upcoming goals for the mission. So please help me in welcoming Dr. Eldering.
All right. Thank you, Mike, and thank you for everyone who's spending their evening hours hanging out here at Caltech with us, and Michelle and the whole Keck Institute staff to make this possible. We're really excited about what we're doing here on the OCO-3 mission. Happy to have an opportunity to share some of our new information and get everybody up to date. So just so I know my audience a little bit, do I have anyone who's a scientist or an engineer in the room? Okay. And how about anyone who follows news on climate and climate science? Excellent. All right, good. So you're here for the right topic and a good lecture. So let me tell you a little bit about what we're doing. And as Mike mentioned, I came here to Caltech, we won't talk about how many years ago that was, to study air pollution. Those of us who've been around for a while remember the days when you'd step outside onto the Caltech campus, look towards the San Gabriel Mountains and not see a thing because it was so darn smoggy. So I came here to work on that stuff, and random events ended up at JPL. I work on these space missions. I'm the one who got the opportunity to come down here, but there are a huge team of people, just really bright, great team, hardworking. It's got to be one of the best jobs in the world. So I'm here to tell you about what all of us are doing together as a team to build this stuff and collect this important data. So let me start here at a sort of a fundamental level with carbon dioxide. This is a graph you've maybe seen before. We call it the Keeling curve. It's a set of measurements taken at Mauna Loa Observatory. Since 1958, they've been measuring carbon dioxide. And you can see on this figure that you've got two lines. There's the black line, which is an average over the year. And you can pretty obviously see this is increasing over time. You've also got this red line that's going up and down because there's this seasonal behavior. So I'm going to explain why those two things are happening. And a number to keep in your head when you're thinking about some of this is 414. That was the May average concentration of carbon dioxide in the atmosphere at Mauna Loa. So why do we have this increase, and why do I have this up and down? So the up and down is almost the easy part. You may be thinking about carbon dioxide and driving your car and power plants, but you can't think about carbon dioxide without thinking about plants and trees and the ocean and the natural system of the Earth. So this up and down that you see from each season to season is really driven by plants' behavior. In the spring, they're growing, they're making leaves, and they're taking carbon dioxide out of the atmosphere. This is a very strong effect in the summertime, and by the time you get to the fall, they sort of stop producing so much, the leaves are starting to die, they're not removing carbon dioxide. And by winter, those leaves decay and actually release carbon dioxide back up in the atmosphere. And it's almost a balance of uptake and release through the season, so you get this seesawing up and down. Now, another piece of the puzzle about carbon dioxide is what you and I and the folks on the world are doing. So we emit carbon dioxide up into the atmosphere. A current number is about 10 gigatons, and this has been increasing as time goes on. But what happens once that gets in the atmosphere? We find, on average, about half of it staying there, and about a quarter of it's taken out by those trees. So the trees and plants are taking out a little bit more. This is the ocean. The ocean's also taking out a little bit more than it releases on average, and the plants take out a little more than they release on average. So we're really fortunate because that rate of growth is slower than it might be if we didn't have the ocean and the land helping us out a little bit. So that's kind of a big picture how this carbon dioxide release and removal is happening. We have increase, it's not as fast as it might be, but it also has a lot of variability. So if you think about this little balance, we have emissions and uptake, not just by land and ocean, but actually, you think about different parts of the world, the tropics, the extratropics, and that imbalance is leading to the growth. And why do I still worry about how this is all happening? Because every year is different. We have years where the ocean and the land take out 20% of the carbon dioxide instead of half. Other years they take out 80%. And the question we have is, where's this line going to go in the future? If the plants and ocean keep behaving pretty much the same, it'll just continue on this trajectory. But let's say the trees have taken up a lot of extra carbon and they just can't take any more. Suddenly this rate might actually increase. Or the ocean somehow transforms and starts taking lots of carbon out, then we maybe see a slowdown. So where's that going to go in the future? What are the factors that influence it? What can we learn about the land and ocean and the role they're going to play? That's what we're thinking about when we ask these questions. And another thing is that this measurement record I showed you is taken from Hawaii. There's about 100 stations across the globe. And as you can imagine, these are on the land surface somewhere. We don't have buoys flowing out in the ocean, so we don't have a lot of data in many parts of the world. And that's a difficulty in trying to answer our question, is the lack of data. So years and years ago, people in this room were involved, and I wasn't at that time, but I am today. People in this room were involved in this idea of, hey, if I can measure sunlight reflecting down and back up to this instrument, the light's interaction with those molecules. So every molecule has a really particular way of absorbing light, and I could probably find out about carbon dioxide if I measure that light really well. And in fact, we've shown we can. We measure light in 3 bands. So these are figures meant to show you there's places where there's not much light absorption, there's a lot of light absorption, and then there's patterns of light absorption. And this is where oxygen is absorbing in a wavelength like your eye sees. And these are 2 places where carbon dioxide absorbs. One, it absorbs pretty strongly, so you see it's more black, and one, it's less strongly. So these are the keys to making this work, letting reflected sunlight that goes through the atmosphere be a measurement that tells us about carbon dioxide. And since I'm speaking at Caltech, I thought I'd throw a little bit of technical detail, not too much, Michelle, I know. So this is the measurement concept, and then I said we measure reflected sunlight. So the fundamental data we get is light. It's not carbon dioxide, but what we do is we say, well, if I make a best guess about what was in the atmosphere, I can calculate what the radiance might be. If I know the temperature, the water vapor, how the light reflected, I can calculate what I think it should be, calculate how the model behaves, and find out if that looks like what I measured. And if it didn't, I say, well, let me move this parameter a little bit, maybe put a little more water vapor in the atmosphere, or put a little less carbon dioxide, recalculate, and can I match what I measured? And you go through this cycle, and eventually you get the best match you can, and it gives you some estimate of carbon dioxide. So that's kind of this inversion problem we call in the retrieval. So we make these measurements of carbon dioxide, and we showed you the Keeling curve, and it's a really important data set in the whole conversation about carbon dioxide. So we need to know, how do we relate to this Keeling curve and other data sets like it? And we have a really important validation activity based out of Caltech, our Total Carbon Column Observing Network, or TCON. And these instruments, these Fourier transform spectrometers, are the key to that system. They're on the ground, they look at the sun, so they do a similar retrieval problem as our satellite, just from the ground. And we have periodically aircraft flying over them that have flash measurements just like the one at Mauna Loa. So we can tie this ground station through an aircraft back to measurements like Mauna Loa, and we tie our satellite back to this measurement by flying over it, and then we can find a link between all the data sets. So that's kind of a fundamental validation that's key. And one other thing I have to say, we ended up finding out there's more in this data than just the carbon dioxide. I'm sure at some point Michelle will invite another lecturer to tell you all about it. But Christian Frankenberger is a professor at Caltech now, was part of the teams that figured out you can look at plants and see that they're green, But in this data, you can actually see a signal of fluorescence. There's a wavelength of light that's responsible from the fluorescence, and you can see all of this stuff is green, but only this is fluorescing a lot, and these other fields less so. So this is another piece of data that tells you about plant activity, comes out of our measurement, but I'm not going to go into much detail on that one. All right, so let's get to the fun movies. So we put together this cool little movie by gathering the data that was collected by OCO2. So we launched OCO2 almost 5 years ago next week, and have measurements of carbon dioxide around the globe. We've exaggerated the footprint size, but just to give you an idea of the coverage, any one of these maps is showing about 30 days of data. And you can see how we sample through the different seasons. You have winter time now, concentrations are getting higher in the northern hemisphere. That's because no plant activity, we're still burning fossil fuel, carbon dioxide concentrations build up. But watch what happens. Right here it starts getting blue, and these are the plants turning on in the northern hemisphere as spring arrives. They're drawing carbon dioxide out as they grow, and you can see they just bite a hole in that northern hemisphere concentration. So suddenly it becomes low. Then we get some mixing and more movement of air, and you start to see it's a period of year the field is pretty flat and the carbon dioxide concentrations are similar north and south. And then we'll get here in the winter, we'll just go through one more season of the buildup in the northern hemisphere as we get into the winter time. And you can see this year is even warmer colors than last year because every year concentrations are going up a bit. So you see the whole pattern of color will shift to the right. And then we'll hit another springtime here in a minute. We're in May and now June, and you start to see a little bit transformation, and suddenly this is lightening up because of the spring. So the plants are creating this seasonal, what we call the breathing of concentrations that go down and up and down and up. Patterns are different in northern hemisphere than the southern hemisphere. There's fewer plants, there's fewer human emissions, and we see the growth over time. So those big features I pointed out in the Keeling curve are quite apparent in the data that we collect. So we're doing this measurement from space now. We actually get a good understanding of carbon dioxide down to about a part per million out of these concentrations that range from 390 to 415. And let me just show you a couple of little detail examples of that. SIF. So this is a movie of the SIF data that's collected. You also see this seasonality of springtime arriving and the plants waking up, but then they go dormant. The tropics stay pretty alive. There's a lot of photosynthesis related signal there. Spring arrives up in the north. So you see, again, this is a different view of the breathing of the planet as the plants get active and then they become more dormant. So these are two of the nice records we've collected with the OCO2 measurement. And this is our home LA with some of the OCO2 data that was collected. And Florian, who's here with us today, helped put together this info that shows two stripes of data collected, one in the summer and one in the spring. And what we want to highlight is how you see these warmer orange-red colors in Los Angeles as the data gets collected. We can't really do it over the San Gabriels because there's too much terrain and topography, but back in the desert, and look at how much cooler these colors are than what they were in LA. You see the contrast of Los Angeles, where we're trapping the air and all the human emissions, as compared to the desert where there's less human activity and therefore lower concentrations. So this is a nice example of how you can see this few parts per million change over a place like LA. Another researcher from Canada was looking at our data set, and he found evidence of power plant plumes. So this is a stripe of data. It's about 6 miles wide, and in that he sees these enhanced concentrations in the red. So you have concentrations that increase for just this little stripe, and if you model what would a power plant plume look like and compare it to what he actually observed, he estimates from our measurements that he's got emissions that are very close to what the EPA says is power plant reports. So that was a real first to say, yeah, I can see a power plant plume and find out emissions from this measurement data set. And here's a similar example in India where you have concentrations here that are many part per million more than the background. Model what you think you should see, look at what you actually collected, and he again can show that the amount of carbon dioxide being released is pretty close to what was reported. So demonstrating not just measuring these global fields, but even these rather local fields. So I mentioned in the beginning that the plants are really important, and every year can be a little bit different in what happens with the carbon dioxide removal and release, and that's one of the big questions we want to answer. So I'm just going to show you one other example from this OCO2 work before I dive into what we're doing with OCO3. So 2015, 2016, there was a big El Nino that occurred, right? And in El Nino, maybe you and I think, oh great, I'm going to have more snow in Mammoth, it's going to be an awesome ski year. If you live in the tropics, it's a different experience. It tends to be drier and hotter in the tropics during the El Nino. And that has an influence on carbon dioxide. So there was an extra gigaton of carbon dioxide in South America that year. Remember I told you human emissions are 10 gigatons. One extra one was shown up in South America. And they really had a lack of precipitation. The plants couldn't be as active as they normally are. The driest period in the last 30 years, and you could see the plants weren't very active, and they therefore didn't take up the carbon dioxide. So that was a big release in South America. You go along in the tropics and look now in Africa, and these reds are where there's extra carbon dioxide, the blue is where there's less than expected. And this was what we call a decomposition anomaly. So the plants that usually are decaying were decaying even faster than usual. And this was almost a gigaton, about 0.8 over Africa. So another continent shows extra carbon dioxide release. It's a different reason than we saw in South America, but contributing almost a similar level of extra carbon dioxide to the atmosphere. And this was, again, very hot conditions because of the El Nino. And then we're finally going to rotate over to look at Indonesia. And this is interesting because before people used to talk about the tropics if it was all the same thing, but with this new data you can tell different things are happening. Big fires occurred in Indonesia 2015, 2016, releasing a lot of carbon dioxide. Again, this region about 0.8 gigaton. And these were really tremendous fires. We could see this, all the people who measure smoke and other fire emissions saw this, and the second driest period in 30 years. So again, really, really dry conditions because of the El Nino. So we now see these three continents all had change. And why is this so interesting to us? Well, we think about what climate change might do, how might the Earth respond? So warmer, drier conditions are something that's predicted with changing climate. And you can see these three different continents didn't take up as much carbon dioxide as they typically do under warmer, drier conditions. So that's not great news because it gets warmer and drier, they don't take carbon dioxide out, your rate of growth might increase. So this sort of suggests that rate of growth of carbon dioxide could go up in the future with the warmer, drier conditions. And we look forward to getting more data to try to really see if that's true in all circumstances. Are there other cases where something different happens? So let's get to some of the fun stuff. This is the International Space Station, a close-up photograph. No, I didn't get to take it myself. I found it on the web. And this in particular is showing the Japanese experimental module exposed facility. I'll just call it the GEM-EF. So it's a place where you can put instruments in. You'll see that each of these boxes have kind of a similar look because this is designed to specify the way to plug an instrument in. Anyone can build it, and then you go and plug it in up there. In the context of the great old space station, so if you've been watching the World Cup, you'll like to know that this is about as big as the field that those people are playing on. This thing is huge. And we are located here on the GEM-EF in slot number 3, right up in the front. This whole thing is flying down towards the corner of the page. So we just got installed recently. We were launched on May 4th and installed on May 10. I'll show you a few more details on that. So we're in the early days of the OCO3 experiment. And what are we doing with this thing? Well, number one, satellites in space don't last forever. So if you're wise, you get something going and then you get the next one and the next one. So we want to continue this record of measurement. So that's kind of the first objective of OCO3. Keep getting these measurements to answer these questions about how much carbon dioxide is taken up and released in different parts of the world. How does it change from year to year? There's a lot more we're going to do about plants and how they're behaving. There's other instruments on the ISS that have additional type of information, and some of the new ways we might measure will help us get some new insights I'll talk about. And then we also have a new way to measure that's going to let us look a little bit at anthropogenic emissions. So let me talk a little bit about being on the ISS and how we might do these new things, and I'll show you a little bit of also some of the engineering details. So this is a CAD model that shows how we took a spare instrument. So a sad story to share is the original OCO was a mission that was built to be a free flyer and measure carbon dioxide. It was launched in 2009, but there was an issue with the protective cover on our spacecraft that didn't fall off the right way. So the thing never made it up into space, and it fell back down in the ocean in 2009. So a failed launch, but a group of scientists advocated strongly with NASA and said, we really need to know about carbon dioxide. So OCO2 was a rebuild of that original idea. And they said, well, if you're going to build it and there's a risk of a problem, build two at the same time, right? You're working on your workbench, it's cheaper to just build two instead of build one and then go back later and build another one. So we had a spare, and we built up an instrument system around that spare, and that's what OCO3 is. So sorry for the uncreative naming of OCO, OCO2, and OCO3, but we're wrapped up around the spare. So this was a CAD drawing. And this is the real thing with some of the engineers who helped do the assembly. So this was built at JPL over a number of years, tested in a thermal vacuum chamber. We close it up, make it cold, take out the air. It feels like space in there. And you can turn your instrument on and test out some parts about how it's going to perform. And we do some vibration testing to see how it's going to survive launch. So we did all this work to build up our payload, and they took it down to Florida and put blankets on it because it's cold in space. So actually these things get blanketed up, and you can you help keep them a little bit warm. So when we measure from the International Space Station, it's really different than a lot of work that people do with satellites. Usually satellites repeat their paths, but the International Space Station flies in a different way. So over a year, these are all the paths that we're going to fly over and collect data on. So it's really a spider web of measurements, and it's going to be really different. That's why we're excited about some of the new science, because we have a much denser set of places that we're going to capture with this data set. And my one other nerdy slide is a map here that shows you some orbit tracks over a 10-day period. And I've colored them by their hour relative to noon. So the blues are early morning data, the reds are late in the day, and sort of green-yellow is middle of the day. And so you'll see that we actually have data collection occurring everywhere from very early to late in the day over just this 10-day period. And this is totally weird for satellite people. We usually fly around same time every day in these sun-synchronous orbits. So you always get measurements at the same time of day, which can make it easy if you want to look at time series and long-term behavior. ISS is going to sample at many different times a day, and it's going to be really interesting. We talked about plants and how important they are. Well, imagine if we can capture what's the photosynthesis and carbon dioxide activity around the plants early in the day. What are they doing in the middle of the day? What do they do in the afternoon? It's kind of a new way to slice and dice and try to get some insights. Now, guaranteed, some of these effects are a little bit subtle and may be hard to measure, but we're going to work on doing it and try to capture those features from our data set. One other aspect of this is that the ISS only goes from 52 north to 52 south. So we've cleverly plotted this in such a way it's not particularly obvious, but our Canadian colleagues continually point out to us how much of Canada is missed. Southern hemisphere, you're a little bit better. There's only a little bit of the landmass that will miss, but anything north of London, Moscow, and lots of Canada does not get sampled from the space station. All right, so for my engineers in the house, another really cool thing about this is the pointing mirror system. So just briefly in words, we have a system that lets us look anywhere we want. It's got one part that rotates kind of parallel to the surface of our instrument, and one part that rotates in the other plane. And if you can move in both of those directions, you can point anywhere. And we'll do that so we can look at our validation sites. We do that to look at the bright spots from the sun glint on the ocean. And we designed this super cool thing we're going to do with it, where we move it in a series of measurement swaths. So this is showing you I moved in a swath and I make a measurement. As the ISS flies here over LA, it got that data. It pointed and it's going to get this swath, repoints again, get this swath, and a couple more times. I'm showing this 4 times faster than it really happens. We'll need about 2 minutes to do these moves. The PMA, the pointing mirror, will repoint itself in somewhere between 2 and 8 seconds. But when we do these types of measurements, we'll end up with a data set that covers a little region, and that's completely new. If you put this in a map view that you may be more familiar with over LA, those data swaths will cover something like this. Kind of the main urbanized area of Los Angeles gets measured over 2 minutes, roughly 50 miles by 50 miles. So I mentioned that anthropogenic emissions are interesting to us. People have looked at power plants, but that was kind of random good luck that we measured over those power plants. With this, we can actually design and say, we want to look at certain cities, we want to look at some power plants. Somebody I know wants to look at a volcano or two. When there's folks out doing field work, we have actually some of our field work team in the audience today. We'll go make measurements where they're going to be. So we can really focus in on some areas with this data. And a particular question we have is, I mentioned that anthropogenic emissions are kind of a key driver and natural system is a remover. There's cities of the world that are still growing rather rapidly, and some of them aren't that well characterized in terms of emissions. So this will test some ideas that people have of how you might be able to characterize city emissions as a whole from some space-based measurements. So we've got some ideas we really want to test out with this kind of measurement set. And so from any day to day, what we're going to do is put these pieces all together. And in this rather colorful plot, I'm just showing you, for an example day, the ISS orbit tracks here in blue. If we're over land, we typically will measure what we call nadir, just looking straight down. When we're over the water, we have to look for a spot that's bright enough, for the glint spot. And then we'll weave in some of these map areas, like area maps I just showed you, like that one in LA. We've got some sites we've picked out. We've got TCON stations for validation. So there's one here to measure and another one over here. I think this is in Japan. So every day we'll make a plan and we'll gather data in all these kind of modes to build up a new measurement record from OCO3. So this is just a cool little movie. Our system engineer, so he's one of the team members who just worries about all the pieces working together, and he managed to gather together a really nice set of imagery and data to kind of tell the little story of OCO3. So as I mentioned, we began a while ago. This is 2011. That was our team thinking about some of the big questions. The Japanese have always been a really important partner for us because of the GEM-EF. And working out some of our technical details to get up on the ISS. So 2011, we got started with some of the ideas, designed and built various pieces, electronics boxes. This is that pointing mirror system being tested in the lab. Get all those components built and tested as individual items, and now you put the team together and they assemble all of this stuff. So this is over 5 months. We've condensed into like 20 seconds of them testing. They have to lift it and move it, flip it around, get all the electronics in there. And once you do that, the next thing you do is see if it's going to survive. So we take it up the hill, and there's a system at JPL that shakes these things like they are going to be launched. This is the thermal vacuum chamber I mentioned earlier. Get it cold, take the air out and see if it performs. And then it got boxed up and put on a truck to take it to Cape Canaveral. This is a SpaceX trunk where we get installed. We flew up on a SpaceX Falcon 9 rocket. Here's the launch on May 4th. Just incredible. I didn't get to see it, but it was still fun to watch at the bar with all of our buddies. And this is when that Dragon separates. SpaceX has cameras on everything. So you see us from a camera that SpaceX had on their feed, the Dragon capsule flying around. And it's almost caught up to the ISS, and now here it's going to get captured by a robotic arm. That's grabbing a little grapple fixture to hold on to the capsule. So now it's actually connected to the ISS, and then it gets latched in on a latch point so they can remove the materials for the astronauts and the internal experiments. Finally, they get a robotic arm and takes us out. This is about 6 days after we arrived. Takes us out and moves us, but it can't get over to the GEM F, so they actually have to do a handoff from one robotic arm to another robotic arm, and this is about where the handoff happens. And you'll see the images get light and dark because we're going around the Earth, and every 45 minutes we go from light to dark and light to dark. And here it's getting moved over and actually connected. You see these little hooks will come down. So no astronauts involved except from the inside working with the robotic arms if needed. They turn us on. That's the pointing system in its blanket, checking out things. It was like a Saturday morning. The team was turning this on and checking out the system. And so where are we today with this? We're getting ready for carbon dioxide. We've been installed on the space station now since May 10th. You can check out our website for lots of details. And so now we're in this checkout period. So dark green are boxes or parts of our system we've completely checked out and know it's working, like the pointing system and the digital cameras. Some of this in light green we've checked out partway but not completely, like our thermal control and our electronics. And this part's white because we didn't do anything yet. Another way to think about this is our engineering team has a timeline, and this is me being a little bit nervous at the beginning because I'm not sure how things are going. We got to first part of our calibration and it seemed like it's okay, but I'm still a little nervous. Today I'm kind of getting happy because we're going to turn the thing on, and then if we get down here into August, it's going to be like, yes, we did it. So where we are is actually we cooled our detectors. Where is that image? A few hours ago, we actually cooled the detectors yesterday. So to run an instrument in space and collect this really sensitive data of carbon dioxide, you need to run things at very cold temperatures. So we spent a few weeks where we actually kept it at warm temperatures to get any extra water we might have brought out and get it out of the instrument. Yesterday, they cooled down the detectors, and this is what we were doing a few hours ago. We were flying over this part of the Earth, and the first time our instrument was looking down and collecting information, that reflected sunlight I mentioned. This is what the weather looked like. The guys are all super nervous. Are we going to get any good data? So we're hoping, okay, a little part of Texas and Oklahoma we flew over, we might actually have good data, maybe over here in the end of Colorado. So unfortunately, this data was collected a few hours ago. It's still in the pipes, coming down to the ground and going through the data processing. So I can't show you a reflected spectra today, but if you check in with me tomorrow, I'm going to have one. And we're always watching what's going on. This is where the ISS is about now. We have a little program where we always look at predicted orbits and see where things are. So I don't have reflected sunlight, but we did take some pretty pictures. We now realize that when you want to tell people about what you're doing, a pretty picture is really useful. And we have 2 cameras on our instrument. One of them is at the end of the pointing system. It's a full color camera, so it's sort of like just one of those pictures you might take. This is over South America, and you can see some little features in here. And another camera we have is actually very close to the heart of the instrument. So it's back behind the pointing system. And that's why it looks circular, because we have this round baffle that the light's coming through. And it also has features in it. The width of our data set, about 6 miles, is about like that on the scale of these things. So these were some pictures we captured in the 17th of May. And if you put the pieces together, you can see that that external camera and that internal camera actually saw the same thing. So we're lining up these 2 features. They're at different geometries just because of the way they're mounted on the spacecraft. But we've spent actually, why do I not have data to share with you today? Part of that is that we want to know exactly how this pointing system's working. So we had to take a lot of pictures at different angles so we can do these correlations and get all of our pointing straightened out. So that's what we were doing until yesterday. But we will get that spectra down and start making measurements of carbon dioxide. So I hope I get a chance to maybe share again, or at least You'll come check out our website as we progress through things, but we're out to measure carbon dioxide. We're going to get these global picture of carbon dioxide. We're going to get these special little area maps of carbon dioxide. We see fluorescence from plants, and we see different times of the day. Completely new way of looking at what's going on in the world. This snapshot mode we're super excited about. We'll probably exercise that in the next few days and see how it works. And another potential KISS lecture is somebody could tell you about all the cool stuff on the ISS. So the ISS has been around for a long time, but it's really being used as a science platform right now. There's instruments to look at water use of plants and water stress called eco-stress. And JEDI is looking at biomass, how much plant material. We're going to bring carbon dioxide and fluorescence into the picture. So there's really a lot of possibilities for looking at plants and then what their role in the natural carbon cycle is. So I'm going to leave with this picture of, it's not the whole team, it's all the team who was available to gather that day. We put the payload in the truck to get it down to Florida. It takes everything from people working the finances to the engineers and scientists and just tons of folks involved to make this stuff happen. And we're really excited to be here at this point of our project. And again, I'm happy I got the opportunity to tell you about what we were up to and hopefully have time for a few questions. So thank you very much.